Today we'll be working on the following problem. Let E be a Lebesgue measurable set in R1 with Lebesgue measure mu, and then have a positive Lebesgue measure for any lambda between 0 and 1. Show that there exists an open interval I from A to B such that the measure of E intersect I is strictly greater than lambda times the length of the interval. Pause the video if you want to work on this problem by yourself. Okay, let's prove this. So basically, we want to find the interval with this property. First, we can assume mu of E is finite without loss of generality. Why? Because there exists R greater than 0 such that the Lebesgue measure of this open interval intersect E is greater than 0, right? Because otherwise the measure of E would be 0. So then we know this, we can replace E by this. It doesn't impact the solution. We impact the interval we are trying to find. Now, so we are trying to find the interval. Let's see what we have. If we recall, the outer measure of E is defined to be, so the infimum of all of this B sub I minus A sub I, sum them up, where each open interval, let's denote by A sub I to B sub I, and then there is a cover, right? So all of this interval cover this E, and then when have the open cover with open intervals of E, and then we take the infimum of all of their total lengths. This defined to be the outer measure of E. Since E is Lebesgue measurable, we know that mu of E is equal to the outer measure of E, right? So we have all this interval. Our goal is like, we want to pick the interval that satisfy this star condition. So we know from the definition of the infimum, for all epsilon greater than 0, there exists this open cover of E such that this sigma bi minus ai, the total length, is less than mu star of E plus epsilon, right? Because the mu star E is the infimum, and which is the same as mu of E plus epsilon, right? So let's do this. So now from this we want to choose epsilon, suitable epsilon, such that this one of the open interval I sub I is what we want in this condition, right? So let's say if all of this does not satisfy this condition, what do we have? If for all I, bi minus ai times lambda is greater than the measure of E intersect I, right? If this, then what do we have? So if for all I, this inequality holds, then we can sum them up for all the AI, for all the i's. So that would be lambda sigma bi minus a sub I greater or equal than sum of this, right? All right, so now we're trying to find a suitable epsilon so that this will be will not be true for OI, meaning that there exists some I such that you have lambda of BI minus AI less or equal than mu of E intersect AI, which is exactly what this condition is, right? We want to find, for OI, let's see if it's greater or equal than this, so we can find a strict less than 1. So I have this. Now record this, now we can write this. Mu is what? Mu is E intersect the union of all this interval, right? Because E is contained within this union of open intervals, and this can be written as the mu of the union of E intersect each I, right? So from the subadditivity of this Lebesgue measure, this is less or equal than sigma I, and the measure of each E intersect I, right? And then from here, what do we have? Well, we have this less or equal than, we have this, right? So if you look at this, so less or less or this less or equal than, right? So this would be less or equal than lambda times sigma B sub I minus A sub I from here, right? From here. Less or equal than this. But then from this, we would say, strictly less than lambda times mu of E plus epsilon from this condition, right? This condition here. So we combine this. So what do we have? If we solve epsilon, this requires epsilon is greater than 1 over lambda minus 1 times mu E. This requires. But since lambda is arbitrary, right? Since lambda is arbitrary, so if we pick epsilon, we can pick epsilon equals to 1 over lambda minus 1 times mu of E. Then we work backwards. If we pick epsilon equal to this, then we would have this one is not true for OI. Right? So meaning like if we pick this, then there exists I such that lambda BI minus AI is strictly less than mu of E intersect I sub I, right? Because if we pick this, then we can find the open cover of E for all the open interval I sub I, such that this cannot hold for all I. There exists one I, that interval I sub I is what we are looking for, right? So that completes the proof. So now the question we can ask is, what if lambda equals to 1? What happened when lambda equals to 1? Can we always find an open interval which satisfies this star? That will be the problem for next time.